Okay, in this next question, we also have a direct contact type where we're going to find K equilibrium constant from the concentrations at equilibrium. Then we're going to find the standard reduction potential, if you want, E naught of the cell or E of the cell from K, or E naught of a certain couple from K. Now, let's look at the example. An excess of liquid ammonia is added to a solution of Fe3+. So therefore, guys, regardless of the enodes and if they're higher or lower, they already are telling me who's the reactant. So the reactant is mercury and Fe3+. Now, they were nice to you and they gave you an equation, but if they don't give you an equation, you have to figure it out and you can't. Okay. At equilibrium, only 46% of the iron remains. So we have some remaining amount of iron in my solution. And of course, they didn't give you the amount of mercury. But remember, liquids do not get into the equilibrium constant. And therefore, if there's something remaining as a reactant, that does somehow mean that the equilibrium constant K is not a complete reaction. Okay, so verify that the equilibrium constant is 0.205. Notice this is not complete. And get the E naught for one of the couples, which is the mercury couple. We're given the iron couple E naught. Great, so we have the equation, which was already given. Again, if it wasn't given, you would get it, put the mercury going to mercury 2+, and the iron 3+, let it go to iron 2+, and get a balanced equation. We're going to set up, again, initial change at equilibrium, ice tables, and I'm going to put minus 2x plus x plus 2x, and you get at equilibrium 0.01 minus 2x, x, and 2x. Now, why did I leave it in the form of x? Is because definitely my K is not complete, okay? And they did not give me an actual number like the AG question for at equilibrium. They didn't give me the equilibrium concentration yet. So what do you have to do is, what they did give you that 44.6% of the starting concentration of iron remains. Okay, so indirectly, if I have 46% out of 100 from the starting concentration, which is 0.01, okay, then that's 4.6 times 10 to the minus 5 molar remains for the iron. Okay, so they're giving me the amount remaining, but in a form of percent. Okay. Again, here they didn't give us volumes. They gave you concentrations initial, so you don't have to use volumes. In other words, this leftover 0.01 minus 2x is equal to the amount 4.6%. Let that equal, solve for the x, and now once you have the x, that means you actually have every single species in your equation. Go back, this is times 2x, this is simply x, and here we already got that. That was 4.6 times 10 to the minus 5, I have to correct. Here, okay, now substitute in and put all the numbers. For the K equilibrium constant, products divided by reactants at equilibrium, and solve for the K. Indeed, we get the K to be 0.25. Don't forget to square the iron. Okay. Okay. Now, next part, once we have the K, we're going to get the delta E naught for the overall reaction. That's it. You have the total number of electrons here that are transferred, which is 2. Get the delta E naught for the overall reaction from the K, solve for it. Once you have the delta E naught, oopsie, wow, the delta E naught is negative. Interesting, the delta E naught is negative, yet the reaction proceeded. And it, you have some 4.6% left over only for the iron. How is that the case? Well, because the reaction, actually, don't forget, reaction, just because it's not spontaneous, delta E naught is negative, we can't really tell that it's not spontaneous just from the delta E naughts, remember? Because you needed the delta E to know if it's spontaneous or not, okay? So the delta E naught does not tell me if the reaction is spontaneous or not spontaneous. Great. Now, once you have the delta E naught, you have the delta E, the E naught for the iron, we can easily get the E for, or E naught for the mercury. We solve for that and we get the solution, okay? Notice the E for mercury is greater than the E for iron. And so it's actually the mercury should have underwent reduction, not oxidation, under standard conditions. Of course, we are working under non-standard conditions, so it doesn't go in the same way. In this case, it happens that the standard is not the same as the non-standard. Okay. Again, it's not spontaneous under standard. And no matter what, it's very difficult for us in this case to get the E for the corrected E for each of the, because initially I have 0, if you will, like in the initial reaction. I need the concentration of mercury 2+ and the concentration of iron 2+ at equilibrium, or at least initially, in order to get the E for each electrode. And I don't have any of those. So those are really 0, their concentration. So you can't really get the E for each couple, okay, when you have a mixture. Okay, that being said, the last question in this part of this section, which is mixtures in one pot. Okay, so now we have a mixture of a solution of titanium. They gave you the volume and concentration with deuterium oxide, and they gave you the volume and its concentration. And it is buffered at a pH of 4, so I have the H+ concentration. Okay? Nicely, I also have the E naughts for both couples, which is great. We can see that the E naught for deuterium is greater, but again, I'm under non-standard conditions. I cannot just base the reaction on the fact that deuterium has a higher E naught, so it's the oxidant. I cannot just do that, okay? However, because I have a mixture of titanium 2+ with UO2+, that means I can say that these guys are reacting with each other, the UO2+ with the titanium 2+, which is indeed in the direction of gamma according to the E naught values, okay? But, you know, correct chemistry, I can't just base it on the E naughts, okay? Okay, once you have, we're gonna take the UO2 with the uranium 4+, balance that half reaction, go ahead, you do that. Take the titanium half, balance it. You notice that this needs to multiply by a 2+ in order to get a global reaction. Get your global reaction and you are done. Once we have the global reaction, what can we get? We see the answer of the first question, which is what is the global reaction? And your answer is A. Okay, what is now the equilibrium constant of this reaction? All right. we all know that the equilibrium constant can possibly come from this reaction or the concentrations at equilibrium. In this case, we are given the delta E naughts for both couples, and therefore, very simply, the log K will be the number of electron transfer total times the delta E naughts for the two couples. One is a negative, one is a positive, and there's a minus sign between them, or get the E naught separately, divided by 0.592, and you get an answer of 33.7. So for the K, we noticed K is fairly high, and therefore it's a complete reaction. Find the answer, and your answer here is C. 12.3, the concentration of the ions at equilibrium. So here they want you to calculate the equilibrium concentration of all the species. Okay, so you have the initial concentration and you have the overall reaction. So put the overall reaction, get the initial concentrations, which is now corrected for dilution factor because they gave you a volume. So we use the titanium oxide had 25 mils times its original concentration divided by the total volume, which is 50 mils. The deuterium oxide is also, they use 25 mils of a 0.2 molar concentration divided by the total volume, which is 50 mils. So get the initial concentration. That's the ice, initial. You have minus X, plus X is the change, but this is a complete reaction, so you can just go overall complete, do a completion. Who's the limiting reagent? So you take, this is 0.1 divided by 1, this is 0.05 divided by 2. So indeed, my titanium is my limiting reactant, and the overall X, or the moles reacted, is going to be 0.25. Do that separately. And then here you have minus X plus X. Now, what about the H plus concentration? This is a buffered solution, so initial will be the same as the final concentration. Do not change that. Whatever you have initially is also going to be whatever you have in the final solution. Products, here you have X, and here you have 2X, which is the same amount as the titanium. That's now at the end of the reaction, so titanium is 0 here, titanium 2 plus. We don't ever put the word 0. We can find the titanium 2 plus. We have all the rest. We call this 2 epsilon or back reaction. But again, we're just gonna find the titanium 2 plus from K. Find the titanium 2 plus, you have the K, you have all the other species at equilibrium, and therefore you solve for the titanium 2 plus. This is a lot of calculation, guys. On an exam, there is a lot. This is a lot of number crunching, so very big possibility to make mistakes here. Okay, get the titanium 2 plus, try to find that. Of course, you have all of these others, they're right in the table, and find your answer. Your answer will be C.